So Cartan criterion. Technically, the very main theorem in this elementary theory of Lie algebras, classical theory of Lie algebras. It is about actually solvable Lie algebras, slightly more general, but we will need in this form solvable Lie algebras, and there exists a necessary and sufficient condition for Lie algebra to be solvable, and it's called Cartan criterion. There are two Cartan criteria, but this is for solvability. Do you still remember what it is, or what it is about? I don't see a lot of enthusiasm, but still, it is very easy to say. We have a Lie algebra G, and now we take G prime. It is the commutator subalgebra, algebra by commutators. And the condition of solvability of G, according to the Cartan criteria, is that if we take the Killing form B and apply it to two arguments, usually we do with Killing form, and one of those arguments is arbitrary in G, and another one is in G prime, then we get 0. So in notations which are designed to make things less clear, let me look at it. Theorem 2, yes. So G prime is contained in the kernel of B. Actually, in the statement which is formulated, here we consider a representation of an arbitrary algebra G, and we consider actually not so much G as rho is representation. And rho of G. It is a subalgebra of the algebra of matrices. B rho is a form on G. B super rho, so trace G super rho of C eta is trace of rho C composition with rho eta, very simple. And the Lie algebra is solvable if and only if the commutator subalgebra G prime is contained in B rho. So now you cannot say that you don't know what it is, because I have just said this. Now I promised, and very, how to say, impartially did that. I promised to explain that actually technically it's a very important theorem. It can be applied to semi-simple algebras, which is more important. And I said that there is a corollary which I proved using the Cartan criterion, also called Cartan criterion, that a Lie algebra is semi-simple if and only if the Killing form is non-degenerate, kernel is 0. Very important result. Will be used many times. Now, I just want to understand what I need to repeat and what you can pretend that you remember. I said that whatever linear endomorphism, linear self-map of vector space into itself you take, then this falls into the sum, so F falls into the sum of two also endomorphism, S and N. S is because it's semi-simple. Semi-simple means diagonalizable. N is because it's nilpotent. In addition to that, S and N commute with each other. So again, F is S plus N. The commutator of S and N is 0. S is semi-simple. N is nilpotent. In addition to that, this decomposition is unique. It is normally proved for, and I will need this, for in the complex case, when it follows easily from the basic theorems of linear algebra, like Jordan normal form, but also true in the real case, and the transition from the real case to the complex case is always done by the complexification. I will do this many times and not always we'll explain it in all details. So what about this? Can I use this? Or you need additional explanations? So for every f, there exists a unique decomposition. F is equal to S plus N. In some basis, S is a diagonal matrix, N is an upper triangular, a strictly upper triangular matrix. But without any reference to any basis, I can say that S is semi-simple, diagonalizable, N is nilpotent, S commutes with N, and then the decomposition is unique. There are two important properties, both will be used, of this decomposition. And this is more or less all that I did last time. First is that S can be presented as a function of f, but not just function. A polynomial without a constant term. There exists a polynomial of one variable, p, without a constant term is 0. And if you plug S, this polynomial does depend on f, and it is not the same polynomial for the whole set of endomorphisms. But for a given f, you can find the polynomial p, so that S is S is p of f. This is one thing. Another thing which is completely trivial is the following. So f is equal to S plus N. But add f, the commutator operation, which acts not on V, but rather on the space of endomorphisms of V, commuting with f, is also a linear endomorphism of that space. And as such, it also has decomposition into the sum of the semi-simple and nilpotent part. In this R, this add of S and N of the semi-simple and nilpotent part of f. This is very easy to explain as soon as you have uniqueness. This more or less all, at least I don't remember that I did anything else, more or less all that I did last time. Questions? So, are you able to, well, pretend, or maybe it's truth, that you understand this and I don't need to repeat it? Try, please. Now, the proof of Cartan criterion. I looked actually at this proof, very different sources. And it is not the same proof which I am going to present. I believe also, probably also, you know, when you refer to history, 99% cases you are very wrong. But I believe that this is the initial proof given by Cartan. It is based on a lemma from linear algebra. As soon as you have this lemma, you have everything. This lemma does not refer to anything like, well, E-algebras, I don't know what else. Just a lemma which you can explain to anybody who knows the notion of vector space and linear operator. The proof, actually, from my point of view, maybe you will not agree with me, is sort of unusual. This is why it should wait for such a mathematician as Elie Cartan to be proved. So, lemma. I prefer again to use annotations. Yes, it is here. Suppose that we have a vector space V. I do everything over C. Actually, all I will say, including this lemma, is true in the real case, and actually in the case of any field of characteristic 0, and the proof for an algebraically closed field, the proof will be the same as I'm going to show to you. For the field which is not algebraically closed, we need to extend the field to like R to C, something to something similar to the complexification. So, we have this space V. And now we consider, yes, in end V, you can write GLV if you prefer, the set of all endomorphisms of V. You have two spaces. One is them of A and one of V, which is A, which is B. Yes, A is bigger, just subspaces, no conditions. Then you define the following set T. It is a set of all Z, right? No, X in my notation. X, which has the following property. Have the following property. If Y belongs to B, no, to A, then the commutator of X and Y belongs to B. Well, looks strange. You can, if you use the notation add, it will be slightly, slightly easier. You can just say that the operator add A maps A into B. Add X, the operator add X, which acting on and V, maps A into B. It will be slightly shorter, but it is the same. Now the statement. So my lemma says the following. If Z, now again Z, right? Yes, Z belongs to T, and the trace of the product ZU is equal to 0 for any U in T, then Z is nilpotent. Let me say a couple of words, just maybe to make your initial impression that it is some crazy statement. To make it clear why we need something like this. At least it is not surprising that we need this. Because the condition is about traces. All right? What is trace? Trace is the sum of eigenvalues. Almost nothing. Trace. Certainly it is, you are not supposed to think that if the trace is 0, then the operator is nilpotent. Trace 0 is the sum of eigenvalues is 0. Nilpotent, all eigenvalues are 0. Certainly is much. And still here, actually, this is more or less, we need to relate the Killing form to solvability. Well, nilpotency, they relate to each other very much. So we need to have some instrument to derive properties like nilpotency, solvability, nilpotency for specific operators from some condition of traces. And this is what we are going to have. So look at this, and this is the main lemma in the Cartan theory. At least believe me that, agree with me, that this is very much elementary. No, the algebras, I don't know what. We just speak of traces, nilpotency. If you don't like this word, say all eigenvalues are zeros, and this will be the same. Now the proof. I would like to know your opinion about this proof. So, first of all, suppose that this satisfies this condition. Z satisfies this condition, not that is S plus N. S is semi-simple, N is nilpotent, and we want to prove that S is 0. Right? Then, S is diagonalizable. Let's diagonalize it. So we take a basis, E1, N is bad maybe, N is okay, M is not. N we have here. So E1, EM a basis, and S of EI is lambda I. EI by lambda I, yes, is a complex number, right? So we have this bunch of complex numbers. Then we consider the following thing. I'm not sure that you ever consider such a thing. I consider the set of all rational linear combinations of this complex numbers. So L is the set of all if you prefer to have a more sophisticated language, you can say that we consider a rational subspace of, so C is regarded as a vector space over Q, very much infinite dimensional. And we consider a subspace which is spanned by these lambda i's. You still remember what I want to prove? I want to prove that all lambdas are 0. All lambdas are 0, then L is 0, right? This is what I'm going to prove. But I'm going to do slightly different thing, which certainly is equivalent to that. I consider an arbitrary linear function on L. Which means that I assign some rational number to every lambda I. Well, lambda I may be linearly dependent over Q. So this is a right thing to say, that I consider this form just on the space. And I want to prove that F is 0. And this will be my lemma. So I will prove that F is 0. This is an arbitrary linear form on L. If an arbitrary linear form on some vector space is 0, then the space is 0. If the space is 0, then all lambdas are 0. If all lambdas are 0, then S is 0, and then Z is N, and it's nilpotent. This is the language which I'm going to use to prove. Now, I consider a new transformation, T, is N from NV, which is defined, look at this, just in this way, T of EI is F of lambda I, EI. So just I switch the eigenvalues using my form F. Now they are all rational, right? What is the relation between T and S? You have a full right to say that no relation, but I want to say something different. T can be expressed as a polynomial in S without a constant term. And this is very simple. Consider some polynomial Q. You know, yes, I actually want to have this for S and T, for add T. So let me say, there are beautiful operators, add S and add T. They should be applied rather to EIJ. EIJ, this is one entry matrix, and add S and add X there, and this is lambda I, lambda J minus lambda I, lambda M lambda J. EIJ, and this is F. I can write F of lambda I minus lambda J simply because F is linear. Very interesting. At this moment, I want to have add T as a polynomial of add S. Q as P is just a polynomial without a constant term, one variable. To do this, I need just to achieve the following property, that Q of lambda I, right? Yes. J is equal to F lambda I, F lambda I minus lambda J. And because of, so what do I need to say? Certainly this is wonderful, but it's possible that lambda I minus lambda J is equal to some lambda K minus lambda L. But in this case, we have a rational linear dependence between lambda I, lambda j, lambda k, and lambda l, and then the same property will hold for f. So if lambda I minus lambda j is equal to lambda k minus lambda l, then f at lambda I minus f at lambda a is equal to f at lambda k minus f at lambda l. That's okay. And then it's very clear, add S and ST to diagonal matrices. So this holds. Also, it is true that add S is a polynomial of at Z. This we know. This we know from my previous lecture. Okay? Now the following. The fact that Z belongs to G means that at Z takes, I don't remember, A into B or B into A. The notation is somehow A into B. A is bigger, yes. Right? But you know, if you take some endomorphism, which takes this into this, then its square also will take this into this, because B is contained in A. Cube, so on. Any polynomial without constant term. With constant term, it will be worse. So from this, it follows. We move from S to Z to S, and from S to Z, that at T of B is in A, right? That is T belongs to T. Now, by assumption, my main property of Z. Can you see this? Trace. My assumption was that the composition of Z with any element of T have zero trace. In particular with this. Let us compute this wonderful trace. Z, you know, is a matrix in my basis, upper triangular matrix with diagonal entries lambda I, right? T is a diagonal matrix. It could be upper triangle, but diagonal, it's diagonal actually, with the with the diagonal entity f of lambda I, right? So this trace is actually the sum over I, lambda I, and it is zero. Now last blow. Let's apply f to both sides of this equality. Let's apply f to both sides of this equality. This is a rational number, so we need to apply it to this. So from this it follows then f of that is zero, which is f of lambda I squared is zero, which means that f of lambda I is zero for all I. This is the end of the story. You understand? The sum of the squares of f of lambda I is zero, but f of lambda I are not complex numbers. They are real numbers, actually rational numbers, but real definitely. So if the sum of the squares is zero, then all of them are zero. So we have that all f lambda I are zero. We think that f is zero for an f was arbitrary, so all linear forms on L are zero. I have already said this. All linear forms on L are zero, then L is zero, then all lambda i's are zero. What else? N is Z is nilpotent. I don't know whether you ever seen. So here is a step which seemed to me not very, how to say, not very usual, not very common. Is this real rational subspace of C, which is spanned by complex numbers which appear in very natural way, eigenvalues of some operator. Does it remind you of something? No? I can say that approximately the same time, another one of the mathematicians, Max Den, proved the so-called third Hilbert problem. He proved it before it was formulated, actually, although he was a student of Hilbert, and Hilbert could know that. This is about, you know, this geometric fact. You have two polyhedra of the same volume. Maybe a cube and a regular tetrahedron, but the same volume. You want to cut this, one of them, into pieces by planes, as many planes as you wish, and you have a lot of pieces. You want to assemble the other one out of these pieces. It is possible to do if you deal with polygons in the plane. If the polygons have the same area, then it's possible, not very difficult. In space, it is not. And actually, the proof of this conjecture, which became very much popular, I think some 70 years after it was invented, because Virgil of algebraic theory. Yes, then invariant. Have you ever heard of this? It is a very interesting thing. But the whole idea that we have some numbers, real or complex, more real in geometry, and then consider rational linear combinations of such a subspace of, say, real numbers, which is generated by several irrational numbers. This is algebraically was the main idea. Certainly it was elaborated very much. Somehow I think, sometimes I think that maybe at that epoch, this idea did not seem so exotic. Just take a rational subspace of just the space of complex numbers. Good. Any questions about this lemma? Because if we don't have questions, then I will deduce from this immediately the Cartan criterion. Don't have questions, decidedly. Good. So we want to prove the following thing. Is the most general statement. Rho is a representation of a Lie algebra. Now we say that rho of, I'm always afraid to switch notations, which is not desirable. It's here probably. Yes, it is here. Right. The statement is, so theorem, that rho of G is solvable if and only if G prime is contained, yes, which means that if you take two elements of G, one from G prime, one from G, and apply the form B rho to these two elements, you will get 0. Okay? Now, before I prove it, let me say that certainly in this general form it sounds okay, but we don't need this for proving. First, rho representation. It may have kernel. But in this case, we just factorize G over the kernel of this representation, and rho becomes 1 to 1. the theory remains the same. What we know about G prime and B rho is sufficient for that. So we always can assume that rho is actually one-to-one. That G actually is a sub-algebra of GLV. And then instead B rho, okay, let be B rho. And now the real and complex case here are related immediately. If our ground field is real, so G, rho, V, all these objects are real, we can complexify them. You can take G sub C, which is the tensor product of G and C, complexify G, complex algebra. You can complexify V, complex vector space, the same dimension. You can complexify rho, multiply this by the identity of C. Okay, you will get everything the same, but with C as subscript. Also, G prime, the commutator subalgebra. When it complexifies the real algebra, the commutator subalgebra is also complexified. So the same commutators, but now we take complex linear combinations of them. The same with B rho. B rho is the same form, only it is complexified. Now it is a formal complex algebra, but simply the complexification of the form B rho of the real algebra. So we don't need to consider real case separately. It will, the statement in this case will follow from the statement in the complex case. Can I consider this as said? In this case, to prove this, I apply my lemma. Oh, no. If and only if, two directions. In one direction is trivial. Let me begin with this. Certainly, if G rho is solvable, if, no rho anymore. Actually, not precisely no rho, because B rho. It will be the trace not of a joint representation. So rho is an embedding. But still, I denote rho of G and G by the same letter. Now I want to say that if G is solvable, G in, and remember, everything is complex. Then, according to the Lie theorem, every C in G in some basis is an upper triangular matrix. Every eta in G prime is strictly upper triangular matrix. Their product, believe me, is also strictly upper triangular matrix. So it's very obvious that trace C eta is 0. Then so B rho is on G prime. G is 0, and this is precisely what we want. So this direction it is trivial. I could say this from the very beginning. It's more interesting in the opposite direction. So we have that G prime is contained in kernel B rho, and we want to deduce that G is solvable. This is the main thing where we will need this lemma. It's not here anymore, but still. So, apply my lemma. V is my V. A and B will be G and G prime. So what is T now? T is the set of all X. And we said that the commutator of X and C belongs to G prime for every C in G, right? Very interesting. Now I take a Z, and Z will be as X, I want to follow my notations. Yes. Z is Xi eta. Both in G. Then look. Take a U in T. Take this trace, ZU. You can switch Z and U here, trace U times Xi eta. This is the same as trace U Xi eta. This is B row of U Xi eta, and this is zero according to my assumption. So my assumption was, so this belongs to the commutator of Lie algebra. This belongs to the algebra. My assumption was that the B row of this two is zero, right? My statement is okay, and I have that Xi eta is nilpotent. If some of you want to say that not all elements in G prime have the form Xi are commutators, I can say that if Z is not Xi eta, but rather the sum of Xi I and eta I, Xi I and I. If we replace this Z, then in the same way I can prove that this trace is zero. So yes, we have that G prime is nilpotent, which means in turn that G is solvable, because G prime is nilpotent, then dissolvable, and then G is solvable. This is the end of the story. I don't know what else to say to you about this, because I don't want that you think that this is some trivial game. Actually, the main idea here, we take some Z, we replace it by S, then by T. These are very different operators, but we find some common properties. One takes A into B, then another one takes A into B. Our relation between these operators are by means of a polynomial without a constant term. This is okay for this proof. But actually, there is a whole theory. I do not need this, but it exists. Such operators, which can, in proofs, you can substitute one for another one, and the properties will be the same. What is a replica? I even don't want to write it. It's written in my notes, because it goes well. There exists, I don't think Cartan used it, but it exists in a more modern theory. A notion of a replica. What is a replica? Suppose that you have some endomorphism of some vector space V over some field of characteristic 0. I don't think that characteristic not 0, it will work. Then, so this is F. Do you know what F star is? This is the adjoint operator between V star and V star. You can take tensor products, P times V, V, and Q times V prime, V star. The elements of this huge vector space are called tensors of the type PQ. If you have an endomorphism F in the space V, you will get an endomorphism you can denote as F sub PQ in the space of tensors of the type PQ. Now, the definition is G is a replica of F if kernel of GPQ is contained in the contains the kernel of FPQ for every P and Q. this is a formal algebraic definition, maybe not very interesting. But this theory used in the algebra of the algebras. I don't think that I will use it anymore. Maybe this is the only time. Still, it is a classical thing. At least if you ever see this word replica, maybe you'll know what it means. I even gave an exercise to you. The relation that G is a replica of F is transitive but not symmetric. If G is a replica of F, this does mean that F is a replica of V, but the transitivity holds. Good. This is all I wanted to say about this criterion. Now, in the remaining 10 minutes, I will be able to show to you how it works for many important things. So certainly I will never apply this criterion in this form in which I proved it. The result which I value a lot is that a Lie algebra is semi-simple, if and only if the Killing form is non-degenerate. These two things are related immediately. The second one immediately follows from the first one. Yes. So imagine that you have a semi-simple Lie algebra. So G semi-simple. Imagine that you have an ideal in G. So for this G, there is a form B, which is non-degenerate. Not always I will need this. In particular, my first word is about the general case. With respect to, so this form, well, bilinear product, bilinear, yes, such in the product. Very much not necessarily, in the real case, not necessarily positive, but not degenerate in this case. I can consider, in particular, H orthogonal. And it is also an ideal. We proved this actually in a very general case. Orthogonal complement to an ideal is an ideal. Yes, that's all. In the semi-simple case, when the form is non-degenerate, we can say that H and H orthogonal have complementary dimensions. The orthogonal dimension of this is equal to dimension of codimension of this. But in general, when you have a non-positive form, it's not true that the space, a subspace in this orthogonal complement do not have intersection. They may have intersection in linear algebra, but not in this situation. So my first claim is that H, I again want to keep the notations. This is 0. Before that, I want to prove that this is 0. So every element of H commutes with every element of H perpendicular. This will follow from this. So begin with this. Take C from this. Take eta from this. Also take zeta from G. Now I consider C, eta, but eta C, zeta. The invariance property B eta, right? But this is very much 0, because eta is in H orthogonal, and this is from H, right? So this strange thing, the commutator between eta and C, has zero in the commutator. zero value of B with any element in G, right? So actually, this you can say that eta C belongs to kernel of B, which is 0. Which is 0 because B is not degenerate. Here we use that. So we see this, that this is 0. Right? Very interesting. Now this thing. With the kind permission, the intersection of H and H orthogonal lies in both H and H orthogonal. These two things are orthogonal to each other. So this means that the commutator is trivial on this, right? So this is commutative. Well, hence solvable. And we have a solvable ideal in a semi-simple Lie algebra, which is not possible if it is not 0. No commutative ideals, no solvable ideals in G. So this is 0. What we have? We have the following, that G as a Lie algebra is the sum of two mutually orthogonal ideals. And this can be done for every ideal. So as soon as you have an ideal, you have the complement. Just orthogonal ideal. What else can I say? Certainly H is both of them are also semi-simple, because ideals in semi-simple Lie algebras are semi-simple. Also, it is not true in general, and maybe in your lessons in algebra this was said to you 1,000,000 times, that in a ring, in an algebra, an ideal of an ideal is not an ideal. If you have an ideal in algebra A, then an ideal in this ideal is not the ideal in the whole algebra. When you consider semi-simple Lie algebra, you can forget about it. Because if you have an ideal in H, you will also an ideal in G, because G is H plus something else. G is just direct sum. So an ideal of an ideal is, well, one more thing. If you have a semi-simple Lie algebra, G, it's always semi-simple about the time. Yes, I have 2 minutes. Consider G prime. It is an ideal. So G is G plus G prime, excuse me, plus G prime perpendicular. But whatever it is isomorphic to the quotient of this or this. What do you think about the quotient of a Lie algebra over its commutative subalgebra? I personally think this is commutative. Now, factorize, whatever you factorize, over the commutative subgroup, subalgebra, sum, whatever you wish, whatever you have. The quotient will be commutative, right? So this is commutative. Again, have you ever seen commutative ideals in a semi-simple Lie algebra? I personally have never seen them, because they are solvable. So this means that this is 0. This means that G prime is equal to G. Well, the remaining 40 seconds, I can only formulate the last statement. It is very simple, but I don't want to prove it in several seconds. It requires full 3 minutes to be proved. So now it follows from what I said, the following thing. Every semi-simple Lie algebra is a direct sum of simple Lie algebras. This decomposition, simple non-commutative Lie algebras, dimension more than 1. This decomposition is unique, absolutely. And every ideal, we spoke of ideal in semi-simple Lie algebras, are just subsums of this sum. Here with direct sum, take some part of it, it will be an ideal, no other ideals. This is the whole structure of the semi-simple Lie algebras. Yes, and next time we will have to consider Casimir operators. I will prove this, but it's 3 minutes.